First one, if we break it down, where do we start our whole problem? I heard 64.07. I'm going to already freak out because 64.07 is a number. Right? Yes, you may have followed that with a unit, but is that unit relevant to where we should be starting? Where should we be starting? What do we start at the end? Grams of SO2. What did we start with? One molecule of SO2. Okay? The person in green, like mines. Molecule is way too many letters to write out, and so they abbreviated it. Unfortunately, they abbreviated it with a symbol that's already used. We can't do that. Okay? So the symbol that I tend to use for molecule would be MLC. Okay? That's not standard, just happens to be what I use. Is molecule equal to gram? No. So molecule must cancel. Ideally, I get grams of SO2. Okay, for those of you writing down exactly what I write, you might pause. Okay, do we have a direct conversion between molecules and grams? No. Okay, so we have to undo that, and instead of doing to grams, we'll convert molecules into something else. What do we want to convert it to?
Moles.
Okay, I heard moles. Okay, what is our conversion between, and officially this is moles of molecules of SO2.
So that'd be 1 mole of SO2.
1 mole is 6.022 times 10 to the 23rd molecules. And I even included the 20 part this time, for those of you keeping record. What unit would I now have? Moles, technically, of molecules of SO2. Almost everybody will drop the molecule. I'll try and always include that. Okay. Are moles of molecules of SO2 the same thing as grams of SO2? No. So I need to get rid of that. Moles of molecules of SO2. Ideally, I would go to grams of SO2. Do I have that conversion factor? Yes. Where's that found? That is the molar mass coming from the periodic table. Periodic, close enough. Table, which I believe everybody got the same number, 6407. 64.07 grams is 1 mole. What unit would I now have?
Grams of 1 SO2.
Grams of SO2. Is that the answer I wanted?
Yes.
Yes. Kind of makes sense? You might say, well, why do I have to be so nitpicky in the units? The units will tell you how to solve a question. That's why you need to be nitpicky with the units. Okay? That's why I'm pushing you to look at your units and track the units through. By writing the units, that will help you figure out what numbers are supposed to be used. Otherwise, you have to memorize the numbers being used. Okay? And the exact formula for how to solve that one question. Okay? Except if you've gone to the library, tutoring center, they've got this kind of wheel, I like to call it the wheel of death, but they call it a mole wheel, which is this weird tractor trailer looking thing with arrows everywhere. Okay. Each of those arrows goes back and forth, meaning you get 2 questions. Okay? And they're going back and forth from a center point, which means they can go out to 2 more questions. So if you look at all the possible permutations, there's something like 30 to 60 potential different ways to ask the same question or getting at the same content, which means you would have to memorize 60 different formulas. That's a pain in the butt. If you use the units and let the units solve the question for you, there's no more, oh, I have to do this or this or this. It's just, oh, the unit just changes. There's no more formula. It's just that's how you solve. And since I think you've got it, This is what I'm talking about. Kind of looks like a wheel of tractor of death. It can't be really a wheel of death because it's got two wheels, right, with all the little arrows and things stabbing out of it. Okay. It can be useful. Some people like it. I personally don't. Okay, but it can be useful. Okay. So take advantage. Go to the tutoring center. See what they have to present. Maybe they'll set it up in a slightly different format that makes more sense to you. Okay. But the unit method is how I'm going to present it in class, and we will always go through the units. Always painstakingly through the units. Make sense? Okay, so let's clean everything up. As far as the rest of those questions, when did we talk about the rest of those questions? Oh, they were in the lecture. This was a really dumb quiz. Those were supposed to be new questions, and I wasn't paying attention at all. All you had to do was write down pretty much your notes from the previous lecture. Okay? So, continuing on. What we're going to move into is now Chapter 9. Chapter 8 is introducing the concept of a mole. Okay? We really then just accept that moles exist and that they work for us. Okay? They're just a large number of something, just like a dozen, and we just kind of accept that and move on. Really what the mole is doing is scaling atoms up to a level that we can now measure. That's the whole point of a mole. Right? And once we're there, because the mole is the same for all substances, I can now just compare moles instead of comparing atoms or molecules. Right? Because the atoms and molecules I can't individually grab a hold of, I can't individually measure. Right? So what do I do once I have an atom or a molecule? Well, I can react it with something else to make a new thing. And so really what we're looking at in Chapter 9 is the same thing we looked at in Chapter 7, equations, chemical reactions. But now the question is, how do we use those or manipulate those in conversions? Well, an equation is just a recipe. Right? You look up a recipe to make a sandwich. Right? If you now want to make 20 recipes, or 20 sandwiches, do you need to look up the recipe to make 20 sandwiches?
Are they different sandwiches?
Same sandwich.
No.
You just change the ingredients. You just scale them upwards. By what? However many. So when making a sandwich, how are we measuring out the bread? I want to make a sandwich. Tell me how to make a sandwich. Cheese sandwich. Make it simple. 2 pieces of bread, sliced cheese, a little bit of mustard, maybe a pickle. No. Keep it simple. 2 pieces of bread, sliced cheese. Smash them together, cheese sandwich. Beautiful. Nobody shouted out, you needed 200 grams of bread. Why not?
We don't know it is 200 grams, we know it is 2 slices.
We can count the slices a whole heck of a lot easier. So when we're going through to make one sandwich, it's not 500 grams of sandwich, it's one sandwich. I'm counting the object. An equation is a count, the number of things. And this immediately becomes problematic when we look at chemistry because I want to react 2 atoms. How do I get a hold of those 2 atoms? Really, 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 really tiny tweezers. Okay. We can't react atoms. Right? At least none of you will probably react atoms, maybe in your lifetime. Okay. We're starting to get close to that, okay? But we aren't there yet. Okay. We're not reacting atoms, we're reacting lots of atoms. We bring a whole bunch of atoms together and we say, do some magic stuff where you guys pair up, and then I will take those proceeds outwards. Okay? We have virtually zero control over that. We just smash them all into one place and then say, do it. Just do it. And then give it to me. Okay? So if we can't count those individual atoms, we have to go through it based off of a scale. We have to scale that up to a point where we can measure it. That's where we bring in the grams. But then the problem with grams is, do we use grams in our equation? No. The numbers in our equation are the number of individual molecules. Okay? But we don't want to use molecules because they're too tiny. So we end up using moles. It's a consistent numbering of that. Okay? It allows me to change that scale to an appropriate value so that I can go through and do some relationships. Okay? So if I needed to build this wheel, what do I need to do? I need the spokes in the wheel. So what would my formula for the wheel be?
However many spokes you have.
Right, however many spokes is probably 32. So I take 32 spokes. I could write out spokes each and every single time, but that gets tedious. So what do we come up with? We come up with some kind of abbreviation. We could call it S, but then it might get confused with sulfur. So we can't use that one because someone else already picked it. So what do we use? SP, because
It's not used.
it's not used, right? I didn't think it was used. It's not used. So there we go. We have a new notation, SP, representing spokes. What do we do with those 32 spokes?
Add a hub.
Right? We're just going to say add a rim, again, for simplicity.
Okay.
Okay? So we add a rim. So we could use R. What's the issue with R? Actually, there isn't an issue with R, is there? No, I think we're okay saying R. How many rims do we need? One. We add those together, and what do we make?
Wheel.
We could call it one wheel. Okay. The problem with this notation is that I'm now adding a new symbol for every single thing I make. Okay. If I only make 20 things, that's not a big deal. What if I make everything known to existence? That's a lot of new symbols. That's a lot of new symbols. So I want to come up with a new notation that says I don't have to create new symbols. I can create new compounds by referencing the components that went into it. So instead of saying one wheel, I can call this one SPR. So to make my wheel, I just need one spoke and one rim. Right? There's only one spoke and one rim in my formula. I would need 32 spokes and one rim, and I now have my wheel. Okay? So chemistry is inventing a system here that allows me to take some basic pieces by some 118 basic pieces, and with that being able to combine in a formula to make now all things known to existence. Some of those formulas get insanely complicated, right? And that's when we start inventing new terms. Okay? But for the most part, that holds. Well, what did I just show here? What did I just build? True. Formula for a wheel. What else? An equation. I have a chemical equation. What if I give you 32 grams of spokes? How many wheels can you make? How many grams is a spoke? Is a good response question to that. We don't know that relationship. We'd have to quantify it. Once I've quantified it, you can then convert the mass into the number, and then you can convert across through the equation. So your equation gives you some kind of basic component information on how to convert between substances. Okay? And up to this point, we didn't really have a way to convert between substances. Now we do. Right? So if I gave you 32 grams of spokes, and I wanted to convert that into the number of spokes, okay, what do I need to know? The mass per number of spoke. Let's say it's 1. Let's not pick gross numbers. Let's pick 2 grams per 1 spoke. How many spokes do I have? 16. Okay, that was chapter 8. Chapter 9 is then asking, instead of converting it into spokes, I want to convert it into the number of my wheels. Well, the number of spokes equal to the number of wheels. Where do I get those numbers? That's what the balanced equation gives me. And in that balanced equation, what are those numbers?
16 on the bottom.
Careful.
No, it's 432.
What are we relating? We're relating spokes to wheels,
So,
which comes from the equation. And in the equation, what's in front of spokes? 32.
Now we're going back. Okay.
What's in front of wheels? 1. I now have a way to convert my spokes into wheels. What becomes a problem now when we look at our answer?
it's only half a wheel.
This says I only get half a wheel. Everybody see that? Okay, or 0.5 wheels. That's really problematic. We can't do that. Okay, that doesn't work. Okay, but this is where chemistry comes in. Chemistry is saying when we run this reaction, I'm not taking 32 spokes, I'm taking 32 moles of spokes. Okay? I'm not taking making one wheel, I'm making 1 mole of wheels. Which then means when I get to the answer, it's not 0.5 wheels, it's 0.5 moles of wheels. What the hell's a mole? 6.022 times 10 to the 23rd. Can I have half of a really massive number? Yes. That's all fair game. So it allows me to come up with fractional values. You might say, well, I can't possibly have a fraction of a molecule. You're not taking a fraction of a molecule. You're taking a fraction of a mole. Okay? By scaling it into that mole level, we can now run these conversions fairly well. Okay? And it allows us to now convert between substances and masses, okay, and atoms if we so chose, but it's usually a bad idea. Okay? And that's pretty awesome. Okay? So let's take a look at some of the strengths. If we take a look at a mole of CO2, how many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? Oh, these stupid word problems. All right, well, set it up. See what we've got. What are we trying to solve for? We need the measurement, moles, the substance CO2. What am I starting with? Moles of sodium hydrogen carbonate. 1 mole. Are the moles of sodium hydrogen carbonate the same as the moles of CO2? No, so I need a conversion factor. I need that conversion factor that allows me to convert between one substance and another. Okay, well, to convert between substances, what must I be looking at? Okay, I need more space. What's that? What do I need? I didn't hear what you said. Go for it. So we had 2 guesses. Usually people guess letters before they start jumping in. And I guess since I already drew the E, I should do that. Someone want to put it all together?
T.
Crap.
Equation.
Fudge.
Okay, it is. You wanted why we weren't like participating.
I'll take the blame on that one. We need a reaction equation. Okay, conveniently for this question, what is provided right above it? A reaction equation. Okay. And I believe Brooke mentioned an extra word. You didn't say just a reaction equation. What did you add in front of it? it must be balanced. If it's not balanced, I can't manipulate or I can't have that conversion. Okay? We don't tell someone to make a sandwich, you only need 1 slice of bread. Your recipe is 2 slices of bread. So given 1 slice, that doesn't work. Okay? We need to have the balanced reaction equation. So we would go back to our question or the context of it, and we're given an equation up top, and it was balanced for us. How do we know what numbers to include? Well, what number shows up in front of sodium hydrogen carbonate? 2. So guess what number shows up in front of sodium hydrogen carbonate? 2. What number shows up in front of CO2 in the equation?
1.
What shows up in front of CO2 in the reaction or calculation? 1. What happens to our units? The moles of sodium hydrogen, the bottom one and the top one cancel. And we end up with moles of CO2. The equation gives us that conversion factor. If we don't have the equation, we cannot solve. Okay? We have to know the relationship between those substances. That's what the equation provides. Okay? Questions on that? Okay, so what is the mass in grams? Let's give you guys a shot at this one. What is the mass in grams of sodium hydrogen carbonate produced when 2 moles of CO2 are consumed? We'll set it up as the basic parts first. What are we trying to get as an answer? Grams of sodium hydrogen carbonate. What are we starting with? We're starting with moles of CO2. There just happens to be 2 of them. Okay? Take a swing at trying to get this one solved out. If you've got questions, raise your hand. Are moles of CO2 the same thing as grams of sodium hydrogen carbonate? No. So I need to do a conversion. Ideally, I would convert moles of CO2 into what? Ideally, grams of sodium hydrogen carbonate. Can I do that conversion? No. So I have to convert the moles of CO2 into something. The question becomes what? Okay. I've got 2 options that I can play with. I can either convert, bless you, the moles into grams, or I can convert the CO2, or convert the substance. So I can either convert the measurement or the substance first, as far as a focus. To convert the substance, what measurement must I be in? Moles. So if I convert moles into grams, can I convert the substance anymore? No. Okay, so maybe I should convert the substance first, because I'm already in the unit I need to convert substances. Okay? So that means keeping the measurement, moles, and getting the new unit, or the new substance, which would be sodium hydrogen carbonate. What is the conversion factor between those? This comes from our balanced equation. 2 shows up in front of our sodium hydrogen carbonate. 1 shows up in front of our CO2. What unit do I have? Moles of sodium hydrogen carbonate. Is that what I want for an answer? No. So I need another conversion. In that conversion, moles of sodium hydrogen carbonate must disappear. What am I hoping? I don't accept that. Grams of sodium hydrogen carbonate. Do I have that conversion factor? Yes. Where? The periodic table gives that to me. So I would add that up. What is sodium? 22 and 23. Plus 1 plus 12 plus 48. Which equals 80? 84 grams per mole. What shows up in front of grams? 84. What shows up in front of moles? 1. I'm trusting that 84 was correct, by the way.
It's actually 84.01 for being technical.
Okay, so let's address that technicality here in just a second.
Unless we're using...
Okay. And we'd go through and we'd calculate and we could get our answer. Okay. This is where this problem goes all sorts of sideways because what would you tell me? Sig figs, which is fun because you can tell how much I pay attention to sig figs because I only gave you one sig fig, which then means your answer needs to get reported to one sig fig, and that would be all sorts of weird. The 84 is not an answer. That's a conversion factor. So the conversion factor must have more sig figs than the unit or than my minimum amount of sig figs. Okay, so this 2 to 1 has how many sig figs? It's infinite. It's the exact number of molecules necessary to do the conversion. So the 2 to 1 is infinite. The 84, I've written it as 2. Okay? That is generally frowned upon in general chemistry. Generally. Okay? And we should carry at least 3 sig figs, if not 4. Okay? Which is what Aspen was calling me out on. 84 point what? 01. You can tell how much I care about sig figs because how much does that change my mathematical answer? Virtually nothing. The amount of time it takes me to enter the 0.01 in the calculator likely means that I will make a mistake. So I personally have made the decision that on a multiple choice test, I don't need that accuracy. I can look to see whatever's closest with rounding on the final answer. This is, again, one of my big issues when it comes to rounding. Number one, I screw up rounding all the time and screw up sig figs. This is something that, unfortunately, your textbook is not consistent in. Future chemistry classes are not consistent in this as well. And they will oscillate between using 84.0, which has slightly less sig figs than 84.01, which means the answer comes out different, which means you go, well, what the heck happened? And usually it was just a rounding issue. Right? Isn't a problem unless you have online homework. All chemistry courses use online homework. Okay? So in future chemistry courses, you may need to watch out for your sig figs. Yes, it will become irritating and frustrating to work with. It's one of those things that you just have to accept. Okay? Back to the answer here. We started with only 2 moles of CO2, which has how many sig figs? 1. Which means the answer needs to get reported to 1 sig fig. What does the calculator spit out as the number? I heard 336? 336 probably in change? Okay. ... Okay. Based off how the question was so poorly written, I'm only allowed 1 sig fig, which means my answer can only be that, and my answer becomes 300 grams of sodium hydrogen carbonate, or 3 times 10 to the second grams of sodium hydrogen carbonate. When it comes to your exam, I'm a little bit more careful on the sig figs, and I usually carry through 3 sig figs for everything. That's kind of the standard for this class, is 3 sig figs. So when in doubt, make it 3 sig figs.
If something were to happen like this on exam, would you prefer 300 grams or 3 to the 10 to the second gram? You know what I mean?
So scientific notation versus not scientific notation. Really, the only reason you would shift into scientific notation is if you wanted one of those zeros to be significant but not the other. Okay, and even that doesn't quite work here. Yeah, it does. One to be significant and not the other, you'd shift into scientific notation. Okay, so the only reason to really use scientific notation is when you've got zeros and you're like, some of them are significant and some of them aren't. Okay, otherwise, leave it as the normal number. Okay, or there's so many zeros that you don't want to write them down. Okay, in which case you can shift to powers of 10, and that's really where powers of 10 came into play. Make sense? We good? Okay. I don't know if this is true or not, but it seems, based off of how you guys are working with this, that it seems like you guys have picked up this equation possibility fairly well. So going through and looking at bicycles and what a bicycle means on building doesn't really make sense? Like, you guys got it? You don't need me to do this weird bicycle analogy?
I would prefer it, to be honest.
Okay, so let's take a look. Simple instructions on how to build a bicycle. What do we have to do? I need 2 wheels and a frame. I take those 2 wheels, the frame, I put them together, and I now have, ta-da, a bicycle. Okay. For those of you who know how to build bicycles, keep it simple. Okay. I don't want to draw all the other parts. Okay. So, 2 wheels I could abbreviate. I don't have to draw out each wheel. I can just say 2 wheels. So there's the first abbreviation we would make. Same kind of idea in chemistry. Okay. So someone built 4 bikes. How many wheels and frames were used?
8 wheels, 4 frames.
Okay, I heard 8 wheels and 4 frames. That was an awfully fast calculation. What was your work to do said calculation?
I know how to build a bike, so sorry.
That's fine. Well, and that's the point of this example, is not saying, oh, I just know the answer. You know the answer. Make sure you develop a method that allows you to see that that is the answer. It's all about the method. Okay? We really shouldn't say this. And now we'll start recording again. Focus on the method. The method is the important part.
Okay, so
Okay? So what did we want for an answer?
you need 4 bikes. You want 4 bikes as an answer.
So there's an interesting question. I want 4 bikes as an answer? I want wheels and I want frames as an answer. Okay? So I want wheels and frames? Can I solve a question that's going to give me wheels and frames as an answer? No. It's 2 separate questions. Both of those questions are starting with what? 4 bikes. What am I then doing to those 4 bikes?
Breaking them down, taking them apart.
I'm looking at the equation that allows me to convert bikes into
Parts.
wheels. Well, according to my equation, how many wheels do I need? 2 wheels, 1 bike. And 4 times 2, amazingly, was 8 wheels. And so the answer that Jerry shouted out right, awesome, great. I knew you could do that, but it's the method. What's happening in the next one? Well, I don't want bikes as an answer. I want frames. What's my conversion factor? 1 frame, 1 bike. And I end up with 4 frames. Okay? Bikes or sandwiches are easier for us to manipulate because all of us can pick up a bike or pick up a sandwich. Most of us have used both. Okay? So we have a better context. We can't do that with chemistry. We have a black box and something's happening within it, and we're guessing at what's happening. We're making observations, and based off those observations, have drawn parallels back to things that we can work with. Okay? So 6 wheels and 3 frames. How many bikes can be made?
We need to find out how many bikes we want.
So bikes is our answer. What are we starting with?
6 wheels and 3 frames, so 2 different equations.
Good. We again have 2 different equations. The wheels and frames are running in different systems. Because what I'm going to assume when I look at the wheels is that wheels is the limiting factor within this. I want to get rid of wheels, and what do I want?
Bikes.
Sorry, I should say bikes. Did I write bikes? I did. 1 bike, 2 wheels. And I get 3 bikes. In the other case, what happens? Frames. Bikes. 1 to 1, I get 3 bikes. Either way we look at it, we still get 3 bikes. So it's taking advantage of the equation and allowing us to do those conversions to set it up. Okay? Given just 2 wheels, how many bikes can be made? There's no frames now specified in this. Okay? Given 2 wheels and an infinite amount of frames, 1 bike. Okay? So when we make statements about given this many grams of a product or starting material, how much of this thing can be made, unfortunately, what we're doing is implying an infinite amount of everything else. Okay? 3 wheels and 2 frames, how many bikes can be made? Okay. Well, 2 frames generates 2 bikes, right? I don't have enough wheels. So we're looking at solving both expressions and saying what's the maximum amount that could possibly come out of this before I run out of materials. Does that make sense? Okay, and I believe last one, 40 grams of wheels and 15 pounds of frames. How many bikes can be made? We don't know because we need to know the weight to numerical value of each of those. We have to do that extra conversion factor. Okay, you might say, well, no one's ever going to go through and say, I've got 40 grams of wheels. How many bikes can be made? What if you're a bicycle manufacturer? You're probably buying things by the pound. You're probably buying several 100,000 pounds of wheels. And you've made an approximation based off of each wheel weighing roughly this much. That means that many wheels. That means that many bikes can be made.
You build
Okay.
wheels out of carbon fiber.
Well, for this, yes. Okay. So it's a question of looking at the scale behind this. Okay. We're trying to build a method that allows me to go from simple stuff, okay, and convert things, incredibly small things, up to a reasonable value. And I can also use this the same way. I can look at incredibly large amounts of things I can manipulate, okay, and scale them down to something that's more reasonable to work with. Okay. But I need each and every single one of those conversions. Okay. What does our equation give us? Well, the equation gives us all of these individual conversions. Okay. From that equation, I know that if I have 2 molecules of NO, I need 1 molecule of O2. Why? What is a molecule? A single unit. Okay. We look at the bottom of that. I have 2 moles equals 1 mole. Why is that true? Well, what is a mole? A really large number of molecules. The ratio maintains the same all the way through. Okay. So depending on what I'm working with or what unit I'm working with, my equation can convert any of those things across because those are all equalities. Okay. Which can be really nice, but how often are we going to work with a molecule? Probably never, because it's tiny. How often are we going to work with 2,000 molecules? A mole was 10 to the 23rd. 2,000 is 10 to the 3rd. Yeah, that's a little small. So I won't work with 2,000 molecules. 12.04 times 10 to the 23rd molecules, that's on the right ballpark, right? 10 to the 23rd. That's now working at a scale I can work with. But the issue with working with that many molecules is what happens. Every time I do a conversion, what must I include? 10 to the 23rd. How many of you like exponents? So it's your fault we're dealing with moles. Not my fault. You didn't want to deal with 10 to the 23rd. If you want to deal with 10 to the 23rd, we didn't have moles. Okay? Moles are there just to simplify that number and get it into a reasonable value. Because if we take each of those numbers and divide by Avogadro's number, 6.022 times 10 to the 23rd, what happens? 2, 1, 2. Okay? That's the point of moles. Is when we get up to a scale that we can actually work with, we have such a large number of molecules that we don't want to mess with the powers of 10. So we invented a new unit. Okay? In and of itself, that's a really kind of neat observation, but then we largely ignore it because we always work in moles. Okay? So you hear some people shout, oh yeah, it's mole day, woo! Yeah, you can tell my enthusiasm. Yeah, I don't really care. Okay? Yes, that's an important value, but it's not something that a chemist uses as a conversion factor really ever, because we just get into moles and we stay in moles. Okay? So, mole relationships. Okay? I'll refer to them as mole relationships. Sometimes your textbook refers to them as unit factors. What are some unit factors that come out of that equation? So it's also known as a mole relationship. I could give you one way to write the mole relationship. 1 mole of N2 equals 1 mole of O2. But that is not a ratio.
So like that as a conversion.
So I could divide both sides, and I can say 1 mole of O2 equals 1. I now have a unit factor that allows me to relate moles of N2 to moles of O2. That's unit factor number 1. List out some other unit factors. See what you come up with. And actually, I'm mildly curious to see what you come up with. So let's try the left one. I need a little bit more directions than that.
Oh, duh.
Yeah, the bottom right.
Yeah.
Bottom right is wrong. So a couple things that we'll draw attention to. Okay. What does the first one equal numerically? What does the second one equal? What is the top middle one equal?
What?
1. Okay. For everybody saying 0.5, what did you do? You did 1 divided by 2. What happened to the units? By you dividing 1 by 2 and then getting rid of the units, you've gotten 0.5. But you got rid of the units. Are those units the same? No. All of these, by definition, equal 1. That's why we can use them as conversion factors. By inserting these into an equation where the units can then cancel, I can then do mathematics. But until the units cancel, these all must equal 1. Okay? And that does look weird because 1 divided by 2, 1 divided by 2 is not 1. That's true. 1 mole of N2 divided by 2 moles of NO is 1. Okay? So you have to be careful in the meaning behind the unit factor. Okay? The unit factor is by definition 1, and that comes from where we started, which was the equality. So let's take a look at that lower right-hand corner. We take 1 mole of N2. Where did I get the 1 from? It's the coefficient from the balanced equation. Equals moles of NO. What number should show up in front of the moles of NO? 2. If I want to now rearrange that equation mathematically, I can divide both sides by 2 moles of NO. Am I allowed to do that? Yes. And I would end up with my conversion factor on the left-hand side, 1 mole of N2 over 2 moles of NO. That's why this is wrong. Except they did O2. Oh well. Equals what? 1. The moles of NO cancel, 2's cancel, and we would get 1. Right? If we take a look at the one that they solved for, the relationship between O2 and NO, we're taking the coefficient in front of O2, which is 1, and the coefficient in front of NO, 2. To fix that conversion factor, to fix the conversion factor, what do we need? 2 moles of NO is 1 mole of O2. Okay? And because that initial equation, I could have divided both sides by the moles of N2, I could have ended up with NO over N2 instead of N2 over NO. Kind of, sort of? Okay.
Wait, are you saying when you're doing it, because you can swap it either way?
You can go either direction. Because of this equality. That equality means I can group those units either on the left-hand side or the right-hand side. If I group them on the right-hand side, what does my equation become? Well, it would be 2 moles of NO, but I'd then be dividing both sides by moles of N2. All right? So it would change my unit factor. Okay? Man, these get so boring. How many moles of oxygen react with 2.25 moles of nitrogen? Set it up, see what you come up with. So, a couple things I want to draw attention to. Write down what you start or what you want, moles of O2. Okay, I noticed a couple people wrote moles of O, not O2. Why is O2 the correct way to write this? We could say from the equation. The equation is actually giving it to you too. The only way it is oxygen atom is it will say oxygen atom. Otherwise, it is assumed to be oxygen, the element, which is diatomic. It's one of our diatomic elements, which means O2 is what we're ending with. Same deal goes with the nitrogen. It's N2, not just because of the equation, but because it's not saying nitrogen atom. Okay, it's saying nitrogen. If we set it up, we write down what we started with, moles of N2. We want the moles of N2 to cancel, to leave us with moles of O2. Where do we find the mole-mole relationship? From our BRE, right? Balanced reaction equation. That's a fun acronym. Just go to BRE. Do we have a BRE in here? We don't have a BRE in here. No. It would be more cool if we had a BRE. What? So, Jake/BRE. What are the numbers that go into our unit factor then? No, seriously, what are the numbers that go into our unit factor? We'll take the numbers from our balanced equation, 1 and 1. And as someone astutely pointed out, that is the exact same. We would end up with 2.25 moles of O2 to react. Okay? It does not have to be difficult. Okay? And you might say, well, isn't that a bit tedious to show all the work? It is tedious now because what we're attempting to do is pick simple questions that you can solve relatively quickly and trustworthy so that you can start to, again, build faith that the method works. That's all we're doing, method. Okay? So we want to do, we could look at what the textbook slides put together. Okay. Moles of CO2 necessary to make 1 mole of sodium hydrogen carbonate. Do you want to solve that one? I think I heard a no. So let's do the harder one. What is the mass in grams of sodium? Did we already do this?
Yes.
No?
Well, it seems.
I thought we did that.
Seems.
Yeah. So this question should look familiar, maybe slightly altered from your exam, but I think it's the same one. Exam 2, for every 1 mole of oxygen consumed, 2 moles of water are produced. If 9 grams of oxygen, which is 16 grams of oxygen equals 1 mole of oxygen, are consumed, then how many grams of water are produced? 18 grams of water equals 1 mole of water. That came off of our exam. What does that now become for exam 3? The exact same question. And yet all of those equalities that showed up in the first one have magically disappeared because you're responsible for knowing where they're found. Since presumably you've not yet memorized all of those answers, and for those of you with computers, please don't look at the previous question. Set this one up. Try and solve it all the way through. If you need to look at the computer, that's fine, but try to avoid looking at all of the conversion factors, primarily because I think one of the conversion factors is wrong. But for an office hours. So what are we trying to get to as an answer? Grams of H2O. What are we starting with? Grams of oxygen gas. Okay. So the first thing that I would identify, we start with substance O2, we end with substance H2O. So we are converting substances. To convert substances, what do we need? Conversion factor found in Mr. BRE. in our balanced reaction equation, which would mean I need a balanced reaction equation. So I'm taking hydrogen gas plus oxygen gas, and I'm reacting that to make H2O. And I go, oh, well, that was dumb. They're all 1-to-1. To balance the oxygen, I need 2 waters, which then means I need 2 hydrogens. It's not 1-to-1 all the way through. Okay? So it's writing down what the equation is and then balancing it. So we do now have that conversion factor. If I was in moles to convert substances, am I in moles?
No.
Nope. So what do I have to do? Convert to moles. So I want to get rid of grams of O2 and make moles of H2O.
So that's not H2, that's just 18 points.
No, I can't do that. The only way I can convert substances is in the same unit. So I'm going to moles of oxygen. I can use the periodic table from chapter 8. And the periodic table would tell me that my answer for that is, I heard 16 grams of oxygen is 1 mole of oxygen. Does anyone want to challenge that? Yin? It's 32. Why is it 32? There's 2 oxygens. It's O2. Watch out for your formulas. We'd be in moles of O2. I want to get rid of, whoops, I made that one awfully big, sorry. I want to get rid of the moles of O2. I can convert that into my moles of H2O because I'm now in the mole unit. The conversion factor, there's 2 moles of water produced for 1 mole of O2. That's coming from my balanced equation. And I now want to get rid of the moles of H2O and get that into grams of H2O. That comes from my periodic table. So that would be 32 again, right? Why not? It's not oxygen gas. It's H2O. So it would be 18, I think 0.01, 02. And we'd now solve. Kind of makes sense?
Yes.
So you're using your balanced reaction equation. You're using the periodic table. You're responsible for all of those conversions. You had to come up with an equation. You had to balance all that equation. All of that stuff has to come together to solve this one question. If that was it, we'd be happy. There is more, but we'll talk about that more on Thursday.